For generations, the cosmos has whispered its grandest question: are we alone? We have built colossal observatories, launched sophisticated probes, and strained our collective ear toward the infinite night, convinced that the answer lies out there, somewhere among the countless stars. Yet the truth, perhaps, begins not in the distant galactic arms, but within the very confines of our own minds, inside the gleaming domes of our telescopes. The quest for extraterrestrial life, far from being an impartial scientific endeavor, is profoundly shaped by a hidden cognitive bias, a fundamental blind spot that dictates where we look and, crucially, what we find. This is the streetlight effect in action, a concept borrowed not from astronomy, but from the everyday psychology of human behavior. It describes the natural human tendency to search for something only where the light is brightest, where it is easiest to look, even if the object of our search is likely elsewhere. When applied to the universe, this seemingly innocuous bias reveals a startling truth. Our methods of exoplanet discovery have created a highly filtered, incomplete reality. We are illuminated by a powerful yet narrow beam of light, and everything outside that beam, no matter how abundant, remains shrouded in shadow. Consider the two primary detection methods that have populated our early catalogs of exoplanets. First, there is the transit method, pioneered by the remarkable Kepler Space Telescope. This ingenious technique works by observing the subtle, almost imperceptible dimming of a star's light as a planet passes directly in front of it, from our perspective. The dip in brightness, perhaps only 1% of the star's total luminosity for a planet like Earth transiting a sun-like star, provides a signature. For the Kepler mission, staring at a patch of sky containing over 150,000 stars, this method proved incredibly effective at finding worlds. Then there is the radial velocity method, often called the wobble method. This technique, which famously led Nobel laureates Michel Mayor and Didier Queloz to their discovery of 51 Pegasi b in 1995, detects the tiny gravitational tug a planet exerts on its parent star. As a planet orbits, it causes its star to wobble ever so slightly, creating a detectable shift in the star's light spectrum, a phenomenon known as the Doppler effect. Both these groundbreaking methods, however, share a fundamental and inescapable bias. They are inherently predisposed to finding massive planets that orbit incredibly close to their stars. Why is this so? A large planet, say, 100 times the mass of Earth, creates a much more pronounced wobble in its star. Similarly, a planet passing very close to its star will transit far more frequently, offering repeated opportunities for detection within a reasonable observation period. This is precisely why our initial understanding of planetary systems was warped by the prevalence of hot Jupiters, bizarre worlds as large as Jupiter, yet orbiting their stars at distances often closer than Mercury is to our own Sun. These colossal, searing hot giants were the easiest targets, the brightest points under our observational streetlight. A small, Earth-like planet, on the other hand, especially one nestled in a wide orbit akin to our own world's 29.8 kilometers per second journey around the Sun, becomes practically invisible to our current technology. Its gravitational tug is minute, its transits infrequent and shallow. It is not necessarily rare, but it is quiet, its presence masked by the sheer scale of cosmic distances and the limitations of our instruments. We are like astronomers trying to hear a whisper from 1,000 miles away, while simultaneously being bombarded by the roar of a jet engine right next to us. The whisper is there, but our ears are simply not yet attuned to its frequency. This observational deafness, this streetlight effect, echoes a fascinating historical parallel from the 19th century. For decades, astronomers wrestled with a perplexing anomaly, the subtle yet persistent deviation in Mercury's orbit around the Sun. Its perihelion, the point of closest approach, was precessing, shifting slightly more than Newton's laws predicted. To explain this, a phantom world was conjured, a planet named Vulcan, supposedly orbiting even closer to the Sun than Mercury. Astronomers, armed with their best calculations and telescopes, observed this world for decades. Reports of its transit across the Sun, flickering against its fiery disk, were numerous. But Vulcan was a ghost, a figment born of expectation. The mystery was only truly solved much later, not by better telescopes, but by Albert Einstein's revolutionary theory of general relativity, which rewrote the very rules of gravity itself. The search for the planet Vulcan serves as a powerful metaphor. Our expectations, our existing frameworks of understanding, can create phantoms in the data, leading us to observe what we believe should be there, rather than what truly is. This profound insight forces us to reevaluate one of the most perplexing mysteries of astrobiology, the great silence of the Fermi Paradox. If the universe is teeming with life, if intelligence is an inevitable outcome of evolution, then where is everyone? Why have we not heard a single signal, a single sign of intelligent brothers from the vast cosmic ocean? Perhaps the great silence is not a cosmic mystery, but rather a direct consequence of our own technological deafness. We are listening in a frequency range we expect, looking for signals that mirror our own, through instruments biased towards what is loud and obvious. To find our intelligent brothers, we must first confront the shadows cast by our own tools and assumptions. We must learn to look, not just where the light is brightest, but to actively peer into the dark, understanding that the most profound truths often reside just beyond the reach of our current perception. For decades, our cosmic searchlight has swept across the galaxy, illuminating the familiar, the sun-like stars, assuming they held the universe's most precious secrets. But what if the greatest treasure, the most abundant real estate for life, has been hiding in plain sight, dismissed as too dim, too turbulent, too alien for complex biology to ever take root? What if the universe's true nurseries, the trillions of cradles for life, are not brilliant yellow suns like our own, but the faint, unassuming glow of red dwarf stars? These M-dwarf stars, accounting for over 75% of all stars in our Milky Way galaxy, have long suffered from a profound prejudice in the astrobiological community. For generations, the prevailing wisdom championed by astronomers like the American scientist Michael Hart in the 1970s was clear: red dwarfs were dead ends for life. Their dimness meant any habitable planet would need to orbit incredibly close, leading to two seemingly insurmountable challenges: permanent tidal locking and devastating stellar flares. Yet, recent breakthroughs and a willingness to question long-held assumptions are shattering this narrow view, recasting these cosmic embers as the most statistically probable cradles of advanced life. First, let us confront the specter of tidal locking. When a planet orbits incredibly close to its star, the star's gravity can eventually lock the planet's rotation, much like our moon is tidally locked to Earth. One side of the planet would perpetually face its star, baked in eternal daylight, while the other would be plunged into endless night, a frozen expanse. This stark dichotomy, a barren wasteland of fire and ice, was long considered a death knell for habitability, but cutting-edge climate models paint a far more nuanced picture. These simulations suggest that a thick atmosphere could effectively redistribute heat around such a world, preventing extreme temperature differentials. Furthermore, a crucial zone emerges, the terminator zone. This is a permanent twilight ring, a perpetual sunset or sunrise, where the star-facing and dark sides meet. Here, temperatures could remain stable, allowing liquid water to exist, and life, perhaps, to thrive in an eternal dusk, adapted to a world without a true day or night cycle. Then there is the formidable problem of stellar flares. Young red dwarfs are notoriously tempestuous, unleashing violent bursts of radiation that could strip away a nascent atmosphere or sterilize any developing life. This genuine concern has fueled much of the historical dismissal. However, studies referencing recent data from NASA's Transiting Exoplanet Survey Satellite, or TSS mission, are revealing a critical detail. Older, more stable red dwarfs are significantly less volatile. The most extreme flaring activity tends to subside after the first few 100 million years of a star's life. Considering that most red dwarfs are ancient, some billions of years older than our Sun, the assumption that all M dwarfs are too dangerous is being systematically dismantled. The calm, ancient red dwarfs vastly outnumber their stormy, youthful counterparts. This brings us to perhaps the most revolutionary idea in the ongoing re-evaluation of red dwarfs: their extraordinary longevity. Our own Sun is a middle-aged star with a lifespan of approximately 10 billion years. Complex life on Earth took roughly 4.5 billion years to emerge, and intelligent life arrived in the final fleeting moments. But red dwarfs are cosmic marathon runners. They burn their nuclear fuel at an incredibly slow rate, allowing them to shine for trillions of years, a timescale so vast it dwarfs the current age of the universe. This immense temporal canvas, a concept thoughtfully explored by thinkers like Avi Loeb of Harvard University, provides a nearly infinite evolutionary sandbox. Imagine the sheer evolutionary possibilities over 100 billion years, or even a trillion years. Such an immense period offers countless opportunities for life to not only arise, but to recover from catastrophic events, to diversify, to complexify, and perhaps to develop intelligence in myriad forms we can scarcely conceive. Consider the TRAPPIST-1 system, a truly astounding discovery. Located only about 40 light-years away, this system hosts 7 Earth-sized planets, all orbiting a single, ultra-cool red dwarf star. 3 of these planets are situated firmly within the star's habitable zone, meaning they could potentially host liquid water. But TRAPPIST-1 is more than just a collection of potentially habitable worlds. It is a profound model for a completely different kind of solar system architecture. Its planets orbit so closely that from the surface of one, its neighbors would appear as large, distinct disks in the sky, some even larger than our own moon. This system is compact, ancient, and offers a glimpse into how common multi-planet systems around red dwarfs might be. This growing understanding fundamentally shifts our mental map of the galaxy. For too long, We have assumed that the prime real estate for life, the most promising locations for finding our intelligent brothers, lies exclusively around sun-like stars. But the evidence now points to the faint, red embers that constitute the vast majority of stellar populations. It urges us to adjust our cosmic compass, to look beyond the brightest lights, and to finally acknowledge the silent potential of the trillion cradles we once ignored. We have scanned the skies for distant signals and pondered the long lives of crimson suns. But what if the most vital secret to finding intelligent brothers lies not in the light from a faraway star, nor in the perfect cosmic address, but deep within the very core of a world itself? What if the true arbiter of a planet's biological potential, the silent engine driving its destiny, is its inner turmoil? Our investigation now shifts dramatically, moving from the ethereal dance of stars and planets to the churning, molten heart of a living world. To grasp this profound truth, we must understand Earth's hidden planetary heartbeat, the carbon-silicate cycle. First comprehensively modeled by pioneering geochemists like James Walker in the 1980s, this intricate process acts as our planet's global thermostat, a planetary regulator that has maintained stable temperatures for billions of years, allowing life to flourish. At its core are the slow, relentless movements of plate tectonics, the majestic drift of continental plates across the planet's surface. These gargantuan slabs of crust, moving at speeds comparable to the growth of your fingernails, perhaps a few centimeters each year, are not merely shifting land masses. They are the essential gears of this cycle, constantly sequestering carbon dioxide from the atmosphere, burying it deep within the Earth's mantle, and then, through volcanic activity, releasing it back into the air. This delicate, eons-long ballet of consumption and exhalation ensures that the planet's climate remains within the narrow, life-sustaining bounds over geological timescales. Without this active, dynamic crust, Earth would have long ago met one of two devastating fates. Consider our closest planetary neighbors, stark reminders of what happens when this internal engine falters. Mars, once a world of flowing rivers and potential oceans, is now a geologically dead husk. Its small size meant its core cooled rapidly, shutting down its internal dynamo. Without plate tectonics, the carbon-silicate cycle ceased. Its atmosphere, once thick enough to support liquid water, slowly but inexorably stripped away by the solar wind, leaving behind a frozen, desolate landscape of rust-colored dust. Conversely, look to Venus, a planet often called Earth's twin due to its similar size. But Venus is a hellscape, its surface hot enough to melt lead, shrouded by an atmosphere 90 times denser than Earth's, composed almost entirely of carbon dioxide. Venus likely possesses a stagnant lid crust. Without active plate tectonics, carbon dioxide released from its interior has nowhere to go but up, trapping heat in a runaway greenhouse effect, a searing testament to a planetary system gone catastrophically wrong. Beyond climate regulation, a planet's molten core performs another absolutely critical function. It generates a global magnetic field. Envision an invisible shield, a colossal protective bubble extending thousands of kilometers into space, deflecting the relentless assault of charged particles streaming from a star, the solar wind. This planetary magnetosphere is a product of a liquid, iron-rich outer core, churning and rotating, creating powerful electric currents that generate the field. The crucial lesson from NASA's MAVEN mission at Mars, launched in 2013, was a stark one. Mars lost its magnetic field early in its history, and that loss directly correlates with the stripping away of its atmosphere by the solar wind, leading to its current uninhabitable state. Earth's robust magnetic field, on the other hand, safeguards our precious atmosphere, providing a continuous, unseen defense against the harsh realities of space. For a long time, the implications of these geological requirements led to a rather pessimistic view of life's prevalence, encapsulated by the rare Earth hypothesis proposed by Peter Ward and Donald Brownlee in 2000. Their argument suggested that the combination of factors necessary for complex life, including a dynamic geology and a strong magnetic field, might be incredibly rare in the cosmos, making Earth a true cosmic anomaly. But recent scientific breakthroughs are starting to challenge this conclusion, hinting at a far more hopeful reality. Contemporary simulations, powered by vast computational models, suggest that super-Earths, a class of exoplanets far more common than Earth-sized worlds, might be even more likely to possess long-lasting plate tectonics and robust magnetic fields. These planets, often 1 to 10 times the mass of Earth, would retain their internal heat for far longer, fueling geological activity for billions, even trillions of years. Their greater gravity could also lead to stronger, more stable crustal plates, yet still capable of subduction and recycling. This means that these super-Earths, once thought of as merely larger versions of our own world, could be superior candidates for the genesis and long-term persistence of life, perhaps even for the evolution of intelligent beings with timescales far beyond our comprehension. A planet, then, is not merely a passive sphere bathed in starlight, but a living, breathing entity, its internal lifeblood pulsing with the essential energy that dictates its surface habitability. We have sifted through the stellar dust, charting the cosmic addresses most likely to cradle life, from the long-lived red dwarf realms to the geologically active super-Earths. But now, with our sights set on these distant, tantalizing worlds, a more profound question emerges. What exactly are we searching for? How do we discern the subtle whisper of life across light years of empty space? The answer lies in the very breath of these planets, in the intricate chemical alphabet woven into their atmospheres, a language only the cutting-edge science of atmospheric spectroscopy can begin to decipher. This is not merely about spotting a single gas, like oxygen, for instance. While oxygen is abundant in Earth's air and crucial for complex life as we know it, its presence alone is not an unambiguous sign of biology at work. Abiotic processes, non-biological chemical reactions, can produce oxygen in significant quantities, especially around certain types of stars or on worlds with specific geological compositions. The universe is far too clever to reveal its secrets with such a simplistic clue. Instead, scientists are now pursuing a far more compelling and robust concept: atmospheric disequilibrium. This powerful idea, championed by visionary scientists like James Lovelock as part of his groundbreaking Gaia hypothesis, posits that a living biosphere is an active, dynamic system, continuously pumping gases into the atmosphere that, by all chemical rights, should not exist together. Consider our own Earth's atmosphere, a volatile cocktail where methane and oxygen coexist. In isolation, these two gases are chemical antagonists. They eagerly react and destroy each other. Yet, here they are, maintained in a delicate, persistent balance by the sheer, overwhelming metabolic output of life itself. This chemical tension, this energetic disequilibrium, is a powerful, almost undeniable signature of a living world, a planetary heartbeat expressed through its atmospheric composition. It is the signature of a system that actively defies the laws of simple chemistry, driven by the ceaseless processes of a global biology. To hunt for these subtle chemical fingerprints, humanity has deployed its most extraordinary eye, the James Webb Space Telescope. With its unparalleled infrared vision, JWST can pierce through the veils of distant planetary atmospheres. As an exoplanet passes in front of its host star, a phenomenon known as a transit, starlight filters through the planet's atmosphere. Different gases absorb different wavelengths of light, leaving unique spectral shadows, like a chemical barcode. JWST is exquisitely designed to detect these minute variations in the infrared spectrum, allowing us to reconstruct the atmospheric composition of worlds tens, even hundreds of light-years away. It is akin to analyzing the exhaust fumes of a car from across a continent, discerning its fuel, its engine's health, and perhaps even the very purpose of its journey. The discussion then naturally evolves beyond biosignatures, the general signs of any life, to the more elusive and tantalizing realm of technosignatures, the unmistakable fingerprints of intelligent industrial civilizations. Drawing inspiration from the groundbreaking work of astrobiologists like Sarah Seeger at the Massachusetts Institute of Technology, we explore the possibility of detecting industrial pollutants in an exoplanet's atmosphere. Think about it. If an advanced civilization is burning fossil fuels or engaging in industrial processes, their skies might be tainted with the very chemicals we, on Earth, struggle to mitigate. Could we detect, for instance, chlorofluorocarbons, or CFCs, those ozone-depleting gases once prevalent in refrigerants and aerosols, or perhaps nitrogen dioxide, a common byproduct of combustion? These are not naturally occurring in significant quantities, making their detection a powerful, almost undeniable smoking gun for a technological presence. It transforms our search into a cosmic forensic investigation, where the atmosphere itself becomes the crime scene, holding clues to a hidden intelligence. One of the most fascinating case studies to emerge from this new wave of atmospheric investigation involves the theoretical Haitian planets. A provocative 2021 study led by researchers at the University of Cambridge proposed that these water-covered worlds, which are larger than Earth but smaller than Neptune, and possess deep global oceans beneath thick, hydrogen-rich atmospheres, could be prime candidates for hosting unique forms of marine life. Even more intriguing, the study suggested that such life might produce distinct biosignatures unlike anything we typically associate with Earth-like worlds. Specifically, they pointed to chemicals like methyl chloride and dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, a tiny, photosynthetic life form at the base of our ocean food chain. Imagine finding these specific chemical suspects in the atmosphere of a Haitian world. It would not only hint at the presence of life, but suggest a vibrant, global aquatic biosphere, profoundly different from our own, yet unequivocally alive. This is the new cartography of our search, no longer a passive hunt for exact Earth clones, but an active, sophisticated forensic investigation, scrutinizing the chemical suspects that betray a living or even an industrial world hidden in the cosmic mists. After searching the cosmos for the right address, the perfect stellar nurseries, and the subtle chemical breath of life, our investigation now reaches a crucial, almost uncomfortable pivot. For centuries, our quest for intelligent beings beyond Earth has been implicitly framed by a single, powerful assumption that they would resemble us. That they would build, communicate, and think in ways we recognize. This anthropocentric lens, fixed on a model of cognition born from our unique evolutionary journey, one centered on tool-making, on radio communication, on a brain housed in a single skull, might be the greatest blind spot in our cosmic search. To truly find our intelligent brothers, we must first dismantle the myth of the toolmaker. Consider the astounding intelligence that flourishes right here on Earth, demonstrating forms of cognition that utterly defy our human-centric definitions. Look at the octopus, a creature of alien grace in our own oceans. Its consciousness is not centralized in a single brain, but distributed throughout its 8 arms, each packed with neurons, capable of independent, localized problem-solving. An octopus can be solving 8 different problems at once, its arms acting with a degree of autonomy that challenges our very understanding of individuality. How would a mind like that build a radio telescope, or communicate through electromagnetic waves? Its reality, its perception of the universe, is so fundamentally different from our own. Then turn your gaze to the seemingly humble ant colony. No single ant possesses what we would term intelligence. Yet collectively, millions of these tiny beings coordinate to build vast, intricate underground cities, forage for food across immense distances, and defend their territory with remarkable efficiency. This collective intelligence, an emergent property of countless simple interactions, allows the colony as a whole to solve complex logistical challenges. It is a brain without a brain, a decision-making entity where consciousness is not localized, but spread across an entire population. What would such a distributed consciousness look like on a planetary scale? Even more bizarre and challenging to our preconceptions are the acellular slime molds. These single-celled organisms, often found creeping across forest floors, are not animals, plants, or fungi. Yet, these pulsating blobs of protoplasm have demonstrated astonishing capabilities. They can navigate complex mazes, find the shortest path between food sources, and even anticipate periodic events, all without a nervous system, without a brain. They learn, they remember, they make decisions, operating on principles we are only just beginning to grasp. If intelligence can manifest in such a primitive, distributed form on Earth, what wonders might await us on other worlds? To frame these revelations, we can turn to a profound biological concept developed by the German biologist Jakob von Uexküll in the early 20th century, the Umwelt. This concept posits that every organism perceives a different subjective universe, a unique reality shaped entirely by its sensory apparatus and its needs. A tick, for example, lives in an Umwelt defined by temperature, butyric acid from mammal sweat, and hair texture. It does not perceive light or sound in the way we do. Its reality is exquisitely tailored to its existence. This idea radically expands our conception of what an intelligent being's reality might be like in the cosmos. Perhaps they perceive the universe through complex magnetic fields, communicating through subtle shifts in planetary energy. Or perhaps their language is a choreographed bioluminescence, a dance of light across an entire world. They might communicate through intricate chemical signals on a planetary scale, like a vast living symphony of scents and tastes. Our limited senses, confined to a narrow band of electromagnetic radiation and a specific range of acoustic frequencies, might render us deaf and blind to their very existence. This forces us to ask provocative questions that dismantle our conventional search strategies. How would we detect a global fungal network that has achieved a collective consciousness, its thoughts unfolding over millennia as it slowly engulfs a planet's subsurface? Its communication might be a chemical whisper, too slow for our fast-paced perception, too subtle for our instruments. How would we recognize a silicon-based life form whose thought processes unfold over geological timescales, its decisions manifesting as slow, deliberate geological shifts or long-term energy reconfigurations? Its intelligence might be so vast, so ponderous, that it is utterly invisible to our fleeting human observation. This intellectual reset demands that we abandon the comforting yet restrictive sci-fi trope of humanoid aliens. It compels us to embrace a vastly wider, far more imaginative, and ultimately, a much more scientifically rigorous spectrum of what intelligent life could truly be. The vast, star-dusted tapestry of the cosmos stretches before us, an unfathomable expanse containing more stars than grains of sand on all the beaches of Earth. If life, even complex, intelligent life, is a natural outcome of evolution, an inevitable byproduct of the universe's grand design, then this infinite canvas should be teeming with voices, a galactic chorus of civilizations. Yet, when we turn our most sensitive ears to the heavens, straining to catch even a whisper of another intelligence, we are met with a profound and unnerving quiet. This is the great silence, the cosmic enigma at the heart of the Fermi Paradox. If they exist, why haven't we heard from them? This question, once confined to the realm of pure astronomy, now forces us to confront not just the physics of the universe, but the chilling sociology, economics, and game theory of contact. For too long, our explanations for this silence have been simplistic, limited to the astronomical. Perhaps intelligent life is incredibly rare, or civilizations always destroy themselves, or the distances are simply too vast. But a far more unsettling and logical answer has emerged from the shadows of science fiction, popularized by the Chinese author Cixin Liu in his chilling novel, The Three-Body Problem, the Dark Forest Hypothesis. This concept fundamentally shifts our perspective, suggesting that the silence is not an absence of life, but rather a deliberate, calculated strategy for survival. It argues that the universe is not a friendly, welcoming neighborhood, but rather a dangerous, predator-filled expanse where survival is the ultimate, non-negotiable imperative for any civilization. The dark forest hypothesis rests on a few core axioms, drawn from the cold, hard logic of game theory. First, every civilization's primary need is to survive and thrive. Second, the resources in the universe, while vast, are ultimately finite, leading to potential competition. Third, and perhaps most terrifyingly, there exists an inescapable chain of suspicion between any two civilizations. The sheer distances involved mean that communication is agonizingly slow, perhaps taking thousands of years for a round-trip message. You can never truly know the intentions of an alien civilization, whether they are peaceful explorers or ravenous conquerors. In a cosmic environment where trust is impossible and intent cannot be verified, the safest strategy for any advanced civilization, upon detecting another, might be to remain absolutely silent and, if possible, eliminate the potential threat immediately and without warning. Consider the classic example from game theory, the prisoner's dilemma. Two suspects are arrested for a crime, but held in separate cells, unable to communicate. Each is offered a deal: betray the other and go free, or stay silent and risk a harsher sentence if the other betrays them. If both betray, both get a moderate sentence. If both stay silent, both get a light sentence. The individually rational choice to betray leads to a worse collective outcome. In the cosmic version of this dilemma, the stakes are not a few years in prison, but the very existence of a civilization. If you announce your presence, you might find a peaceful friend, or you might invite your own destruction. Given the existential risk, the optimal, most rational strategy becomes one of utter paranoia and preemptive action. This stark, logical, and terrifying conclusion provides a potential answer to the great silence. The universe is silent because its inhabitants are smart enough to stay hidden. This chilling logic stands in direct opposition to the more optimistic perspective championed by the messaging extraterrestrial intelligence, or METI, movement. Figures like the Russian astronomer Alexander Zaitsev have passionately argued for proactive broadcasting, for sending deliberate, powerful messages into space, announcing humanity's presence, and extending a hand of friendship across the void. They believe that the benefits of contact, the sharing of knowledge, the overcoming of existential threats, far outweigh the risks. This is not merely a scientific debate about methodology. It is a profound philosophical rift about the very nature of risk, reward, and the ultimate implications of contact. Are we cosmic optimists, or are we naive in a universe that might punish openness? This philosophical tension adds a dramatic new layer to our past attempts at interstellar communication. Consider the Arecibo message, broadcast in 1974 from the colossal Arecibo Observatory in Puerto Rico. This was not a passive listening experiment, but an active, focused beacon of human information, a picture message encoded in binary code, intended for the globular cluster Messier 13, located some 25,000 light-years away. It contained details about our numbering system, the structure of our DNA, humanity's average height, and our solar system. From a traditional perspective, it was a hopeful greeting, a testament to our desire for connection. Yet, when viewed through the lens of the dark forest hypothesis, this act of audacious self-introduction transforms from a hopeful wave into a potentially catastrophic strategic blunder. We screamed our location into a cosmic wilderness without knowing who or what might be listening. The Arecibo message, in this context, becomes a cosmic gamble, a roll of the dice in a game with stakes beyond our current comprehension. The silence in the sky, therefore, might not be an absence of life, but rather the most eloquent and chilling testament to its intelligence. After epochs spent navigating the cosmic currents, refining our charts of the impossible, and learning to read the universe's most subtle whispers, The time has come to point our most powerful eyes not just at abstract theories, but at concrete, tangible worlds. We are no longer simply charting the vast, empty ocean of space. We are finally dropping anchor at specific, tantalizing ports. Our expanded understanding of what life might be, where it might thrive, and even how it might choose to remain silent, now allows us to redefine the very notion of promising. We are moving beyond the simplistic quest for mere Earth clones, venturing into a nuanced cartography of hope, guided by scientific insights that reach far deeper than surface appearances. This is not a mere top 10 list, but rather a collection of cosmic laboratories, each presenting a unique scientific mystery, where the hypotheses forged through our intellectual journey can now be rigorously tested with the advanced instruments at humanity's disposal. First on this new map of cosmic possibility stands K218b, a world that has rapidly ascended to the pinnacle of astrobiological interest. This celestial body, classified as a sub-Neptune, or more intriguingly, a Hyson world, represents a profound departure from our traditional search for Earth-like planets. It is significantly larger than Earth, roughly 2 6/10 times Earth's radius, and approximately 8 6/10 times Earth's mass, placing it in a category of planets entirely absent from our own solar system. This means its very existence challenges our preconceived notions of planetary formation. Its dense, hydrogen-rich atmosphere is believed to shroud a deep, global ocean, a concept that immediately expands the potential definition of a habitable environment beyond terrestrial shores. In the year 2023, the James Webb Space Telescope, humanity's most sensitive infrared eye on the cosmos, delivered truly tantalizing data from K218b. Researchers detected not just water vapor, but carbon-bearing molecules like methane and carbon dioxide in its atmosphere. These are crucial building blocks for life as we know it, but the most electrifying possibility emerged with the tentative detection of dimethyl sulfide. On Earth, this particular molecule is produced almost exclusively by marine phytoplankton, tiny photosynthetic organisms that form the base of our aquatic food chains. If confirmed, the presence of dimethyl sulfide on K218b would be a powerful, almost unambiguous biosignature, suggesting a vast living aquatic biosphere thriving in a hydrogen-rich water world tens of light-years away, offering a starkly different, yet profoundly alive, alternative to our own blue marble. Moving across our revised galactic chart, our gaze settles on Kepler 1649c, an exoplanet that, on the surface, might appear more familiar. It is remarkably similar in size to Earth, with a radius 1.06 times that of our homeworld. But its true significance lies not in its physical dimensions, but in its stellar parentage. Kepler 1649c orbits a red dwarf star, one of those faint, long-lived embers that constitute over 75% of all stars in our Milky Way galaxy. This makes it an invaluable test case for the burgeoning theories that assert these crimson suns, once dismissed as hostile to life, are in fact the galaxy's most statistically probable cradles for complex biology. This planet lies squarely within its star's habitable zone, meaning it could potentially host liquid water on its surface. The crucial next step for missions like the James Webb Space Telescope is to perform precise atmospheric characterization. Can we detect a stable atmosphere rich in the telltale gases that suggest a living world? And crucially, will its atmosphere show signs that it has overcome the intense stellar flares common to younger red dwarfs, or adapted to the tidal locking that might mean one side of the planet perpetually faces its star, creating a unique terminator zone where life might thrive in an eternal twilight? The observations from Kepler 1649c will be critical in validating our understanding of habitability around these ubiquitous, often underestimated, cosmic beacons. Finally, we turn our attention to a more speculative yet immensely fascinating target, a super-Earth known as TOI 1452b. This world, playfully dubbed the ocean planet, captured scientific interest due to its exceptionally low density. With a mass nearly 5 times that of Earth, its density suggests that water could account for a significant fraction of its total mass, perhaps as much as 30%, compared to Earth's mere 0.02%. This implies a world entirely covered by a massive, deep, global ocean, potentially hundreds of kilometers deep, dwarfing Earth's own Mariana Trench, which descends to just shy of 11 kilometers. This planet serves as a perfect laboratory to test our ideas about a planet's internal engine being the true arbiter of its biological potential. If TOI 1452b indeed harbors such a vast aquatic realm, it offers a unique opportunity to search for the chemical byproducts of a global aquatic biosphere. Could a planet so dominated by water still maintain the geological activity necessary for long-term climate regulation, perhaps through a different kind of carbon cycle than Earth's plate tectonics? What distinct biosignatures might emerge from an ocean planet with such immense pressure at its depths? The search for signs of a water-rich atmosphere and the metabolic waste products of a planetary-scale marine ecosystem would reveal whether life, even complex, intelligent life, can emerge and thrive in a cosmos where the deep ocean, rather than dry land, is the dominant feature. These planets, K218b, Kepler 1649c, and TOI 1452b, represent far more than just dots on a star chart. They are the prime suspects in humanity's grandest investigation, each an unfolding scientific mystery. They embody the practical application of our entire intellectual journey, a living, evolving map of promising worlds based on a deeper, more sophisticated understanding of life's potential, challenging us to look beyond the familiar and embrace the wondrous diversity of the cosmos. After journeying through light years and ancient star systems, after scrutinizing the faint whispers of distant worlds, what if the most profound discovery awaiting us lies not in the distant cosmos, but within the very essence of humanity itself? This ultimate quest for intelligent brothers, for life beyond our blue marble, is fundamentally an act of self-reflection, a cosmic mirror held up to our own existence. Every question we project onto the vastness of space, every hypothesis we formulate about alien life, is in truth a question about our own nature, our potential future, and the very meaning of our presence in this universe. Consider the meticulous criteria we have developed for habitability, the precise atmospheric compositions and geological processes we seek on other worlds. In defining what makes an exoplanet a living world, we are simultaneously forced to define what makes Earth uniquely vibrant. We delve into the intricate dance of our planet's fragile geology, the churning heart of plate tectonics, and the delicate balance of a biosphere that has sustained life for billions of years. This comparative study deepens our understanding of Earth not as a mere backdrop for human drama, but as a dynamic, living entity whose internal processes are inextricably linked to the very breath we take. Our pursuit of alien homes sharpens our appreciation for the singular, almost miraculous conditions that allow life to flourish here. Then, recall our exploration into the very nature of alien intelligence, a journey that challenged the narrow, anthropocentric definitions we often cling to. When we grapple with the distributed consciousness of an octopus or the collective problem-solving of a slime mold, we are compelled to confront the inherent limits of our own cognition. We question the assumption that intelligence must reside within a single, tool-making brain, or communicate through radio waves. This intellectual exercise, this attempt to empathize with utterly foreign modes of thought, forces us to reevaluate the immense value and diversity of other forms of consciousness that exist right here on our own planet, often overlooked, often misunderstood. It expands our perception of what knowing and being truly mean. The chilling implications of the dark forest hypothesis, a universe where silence is a strategic imperative, also serve as a profound, almost uncomfortable mirror. When we ponder why advanced civilizations might choose to remain hidden, or even resort to preemptive strikes for survival, we are inevitably holding up a reflection of humanity's own turbulent history of conflict, suspicion, and the anxieties we harbor about our collective future. The cosmic silence, in this context, resonates with our deepest fears and raises a crucial question. If presented with the ultimate choice, would we, as a species, prioritize connection or the brutal logic of self-preservation? This thought experiment is less about alien motivations and more about our own capacity for both destruction and cooperation. Carl Sagan, with his unique blend of scientific rigor and poetic wonder, perhaps understood this introspection better than anyone. He masterfully used the cosmic perspective, the humbling image of our tiny, pale blue dot, not to diminish humanity, but to highlight the extraordinary preciousness and profound unity of all life on Earth. The search for extraterrestrial intelligence, in his view, was never just about finding others. It was about understanding ourselves, about realizing our shared vulnerability and our interconnectedness within the grand cosmic tapestry. It is a reminder that in the face of the universe's immensity, our differences on this small world become insignificant. The search for extraterrestrial life is therefore far more than an astronomical project confined to telescopes and data analysis. It is arguably the grandest interdisciplinary endeavor ever conceived, demanding collaboration that transcends the traditional boundaries of human knowledge. It forces biologists to communicate with geologists, compelling sociologists to engage with philosophers, and engineers to work alongside ethicists. This monumental undertaking unites diverse fields, pulling together the sharpest minds from disparate disciplines, all driven by a singular, overarching question that touches every aspect of what it means to be alive. So, as we continue to scan the heavens, to parse the faint signals from distant stars, and to decode the chemical languages of alien atmospheres, the ultimate goal shifts. It is not simply about discovering whether we are alone in this universe or how many other intelligent species might exist. The true purpose, the enduring legacy of this relentless quest, is to use the vastness of the cosmos as an unparalleled tool for introspection. It compels us to finally understand, with a clarity previously unattainable, what it truly means to be a human, a terrestrial, a transient yet remarkable part of a universe far stranger and infinitely more wonderful than we have yet dared to conceive.